Good morning, Professor and fellow classmates. Welcome to our group presentation for DMI D2853, Mechanics of Materials. Today, our team will take you all through in an in-depth forensic engineering case study analyzing the structural failure and catastrophic collapse of the Silver Bridge, also known as the US 35 highway crossing. Joining me in this investigative breakdown are my team members Lee Long, Muhammad Imran Ryan, Erdina Alia, and not forgetting to mention myself, Rutreshwaran. Together, we will dissect this historic disaster by translating its physical properties into rigorous beam flexing mechanics, verifying its global stress envelopes, and examining how a microscopic connection flow brought down an entire multi-span structure. Let us begin by reviewing the historical background and overview of the suspension system. To understand the context of this collapse, we look at the bridge's physical setting and operational baseline. The Silver Bridge spans across the Ohio River, serving as a critical arterial highway linking Point Pleasant, Virginia to Kanyagu, Ohio, under heavy daily US Road 35 commuter traffic. The turning point occurred on December 15, 1967. During the peak of holiday evening rush hour gridlock, the main suspension system experienced an instantaneous total collapse. The impact was devastatingly swift. Within approximately 60 seconds, the full structural framework disintegrated, plunging 46 vehicles directly into the freezing river and resulting in 46 tragic fatalities. This catastrophic event immediately launched an exhaustive forensic engineering study by the National Transportation Safety Board (NTSB) and the National Bureau of Standards (NBS). Their main objective was to answer a profound engineering paradox. Why did a bridge designed under global standard safety codes fail completely without a warning? To find out, I will hand the floor over to Ryan to discuss the structural specifications.
Thank you, Rutreshwaran. On slide 3, we analyze the structural geometry and material characteristics that define the bridge framework. The primary longitudinal load-bearing structural member was a stiffening hollow box girder. As illustrated in our cross-sectional diagram, the profile features an outer width B of 2 meter and an outer height H of 4 meter, accounting for a steel wall plate thickness T of 0.05 meter or 50 millimeter. The internal hollow core boundaries clear an inner width B of 1.9 meter and an inner height H of 3.9 meter. Metallurgically, the structure was manufactured using heat-treated carbon steel modeled as an ASTM A36 equivalent for our standard mechanics analysis. This profile established our engineering constant, a material yield stress of 250.00 MPa, and a Young modulus E of 200.00 GPa. The neutral axis of ONA passes directly through the geometric center where bending stress equals 0. Now, let's examine the unique suspension system that held this girder profile in place. Slide 4 exposes the core design vulnerability that doomed the structure. Instead of relying on conventional multi-wire wound steel cables, the engineers implemented an innovative I-bar chain link network system to suspend the deck throughs. Looking closely at the critical joint layout shown in plate 2, each unique link in the chain was constructed from just two parallel high-strength steel I-bars pinned together by a massive central steel shaft. When we execute a structural redundancy check on this configuration, we discovered a fatal flaw. The link assembly possessed absolute zero redundancy. Unlike traditional wire cables, where the snapping of individual microwires does not compromise the main suspension line, this design created a strict single point of failure. This posed a massive chain link threat. If one I-bar cracked and failed, the connection pin would instantly tilt asymmetrically under load. This unbalance causes the adjacent twin bar to slip completely off the pin, unzipping the entire suspension chain in a rapid chain reaction. I will now pass the presentation to Irdina to break down our primary mathematical statics.
Thank you, Ryan. To analyze the bridge bending behavior, we first calculate the area moment of inertia for the hollow box girder section by subtracting the inner hollow section. From the outer section, we obtain an inertia value of 1.27 meter power by 4. Besides that, you also determine the maximum bending moment that caused by a traffic load of 18,000 Newton per meter over a 100 meter span. Using the simply supported beam equation, the maximum bending moment at mid-span is 1.0 multiplied 10 power by 8 Newton meter. Actually, this value is represented by the parabolic bending moment diagram that is shown below. Moreover, if you look on slide 6, using the maximum bending moment, we also calculate the maximum bending stress with the Fraser formula. The result is that we got 156.93 megapascal at the outer fibers of the girder. Then compare this stress with the yield strength of ASTM A36 steel, which is 250 megapascal. Since 156.93 megapascal is lower than 250 megapascal, the bridge had a factor of safety of 1.59. Actually, this indicates that the bridge did not fail due to overall bending of the main girder. Therefore, the actual cause of collapse must be related to other structural components such as the gusset plates and local stress concentrations. That's all from me.
Thank you, Idina. To complete our macro mechanic review, we calculate the elastic bending curvature. We use kappa as the symbol, which quantifies global bending deformation. We utilizing our moment rigidity ratios, which is use the moment of the mass divided the component of elasticity times the moment of inertia of the box. So we use the 1 times 10 to the power of 8 Newton meter divided the 200 times the 10 to the power of 9 Pascal times the 1.27 meter power of 4. So we get the final answer, which is 0.00039 meter power of negative 1. As stated in the NDSP session 4B3, this global bending curvature was extremely minor, providing that the bridge does exhibit virtually zero visible warning deflation period to its collapse. However, static equilibrium requires this massive bending loads to be balanced by the suspension change, converting the global moments into a massive axial tension inside the ear bar links, as mapped in our right hand diagram. You can see this layer force the force to transition through the unicircular geometry of the pinhole in ear bar number 330. This geometric change create a severe localized stress concentration factor, serving well past the 3.0. This local stress spike bypassed the global safety factor, triggering plastic micro-yielding right at the joint rim. Over 39 years of repetitive traffic fatigues and stress corrosion crack propagation, this tiny hidden flow expanded until it hit a critical threshold, triggering a sudden, no ductile brittle fracture of the ear band number 330. Because the change had zero redundancy, this single localizers snap chose the entire bridge to unzip intensely. Now we come to the slide X, which summarizes the core forensic lesson learned from these disasters. First, we uncover the illusions of macro safety, proving that a structure is safe under Global bending moments and yield stress calculation is completely meaningless if your localized joint connections are unverified or leave the unmodeled. Second, we see the sovereign danger of non-redundant structural path in the public assembly manufacturing. Single point or the field layers are highly dangerous, which is why modern structural engineering course strictly mandates multiple loop path redundancy to prevent the localized flows from turning into the progressive collapse. Finally, we learned the vector inspirations lesson stress concentrated heavily at the geometry transitions hidden beneath pins, fastener, or covers. Modern assembly standards mandate the use of non-destructive testing, or we call as the short form NDT, such as ultrasonic or the magnetic particle tracking, to actively catch the hidden vertical cracks before they choose the total system fillets. Our analysis is fully backed by the official investigation report from the NTSB, the National Bureau of Standards, and the standard flexural theory from the Hibbett's textbook. So that concludes our group's analysis of the silver bridge structural fillets. Thank you very much for your time and attention. We are now ready and open to take any question from the floats.